All right, this video is going to be on how to compare series and use that as your test for convergence or divergence. All right, so for example, if we were to look at the series 1 over 2 to the n, we would see that it's geometric. But if we looked at the series n over 2 to the n, we would see that it is not geometric, even though they're very similar to each other. If we looked at the series 1 over n to the third, we would see that that is a p-series, and we could check for convergence that way. If we look at the series 1 over n to the third plus 3, we will see that while it's close to a p-series, it is not actually a p-series. I think I said n to the third plus 3, but I meant plus 1. Although plus 3 would be the same thing. If we're looking at the series n over n squared plus 1, you could see that while it's not a p-series, while it's not geometric, while it's not telescoping, we could easily integrate it. So we could do that integral test. But if we look at the series n squared over n squared plus 3 squared, you would find that it is not easily integrated, even though they are somewhat similar. So in this situation where you can see a series that is similar to something we know how to work with, what we'll end up doing is we'll compare them. And we have two different tests we're going to look at. The first one is called the direct comparison test. Or DCT. And the direct comparison test says if you have the inequality where a sub n is between 0 and b sub n, and it has to be greater than 0, it has to be less than or equal to b sub n, for large values of n, so you want to think about it kind of like if you were to evaluate it for infinity or if you were to find the limit of these two, then we have two conclusions. If the series b sub n converges, then a sub n converges as well. If a sub n diverges, then b sub n diverges as well. So you'll notice those are two very specific circumstances, and they don't do like a vice versa sort of thing. So either you can say this one converges, therefore that one converges, or you can say this one diverges, therefore that one diverges. And if it's not one of those two specific circumstances, then this test will not help you. All right, so let's make a note to ourselves to be careful with the inequality. Because you're not going to be able to check, let's say you want to check for divergence, and you find that this one diverges, so you want to conclude that that one diverges. That's not a conclusion we can make based off of this test. So just be careful that you're making the right conclusions. These are two very specific circumstances. All right. So for example, we're going to, for instructions, we're going to determine whether the series converges or diverges. And notice that we haven't said anything about if it converges, this is the value that it converges to, only if it does. So this test is a little bit limited because it just tells us whether it does or not. It doesn't give us more information than that. So for our first example, we're going to look at the series 1 over 2 plus 3 to the n. And we're going to go ahead and do a direct comparison test with the series 1 over 3 to the n, because that's something that we know how to check. This is a geometric sequence, or a geometric series, I mean. And you can see that if you were to rewrite it as 1 over 3 to the n, there's a parenthesis right there, 1 over 3 to the n, that your r value is 1/3. And since your r value is 1/3, then we know that this one right here converges. Right? So now I can say that I'm checking the first circumstance where if I can write it so that b sub n converges, then a sub n will converge as well. That's the inequality that we're trying to use right now. So I'm going to go ahead and set this up. I've got 0 is less than my a sub n, which is less than or equal to my b sub n. And if you think about plugging in infinity here, we would find that this denominator would be slightly bigger than this denominator. It'd be infinity plus 2, and this is just 1 over infinity. So what we would know here is that since this denominator is bigger, that means that this fraction is a little bit smaller, right? So if you think about your fractions, if you had the fractions 4/5, 4/6, I guess, 4/6, and then you compared that with 4/5, 4/6 would be a little bit smaller, right? Because 4/6 is 0.66666, 4/5 is 0.8. All right, so think of it that way. If your denominator is a little bit bigger, then it means your fraction is a little bit smaller. In that case, if you have the same number on top. So our conclusion here, since we know that this converges, then now we know this converges, and so overall, we're going to conclude that original series converges. All right, second example, we're going to look at the series from 1 to infinity of 1 over square root n minus 2. And we're going to do a direct comparison test with the series 1 over square root of n. And the reason we're going to do that direct comparison test is because I can rewrite this as n to the negative 1/2, and that makes it a p series. So it's a p series where p equals negative 1/2, and that's less than 1. And so that, or not negative 1/2. Sorry, I forgot the p series, I already had it on the bottom. It's like something about this seems wrong. So if you guys recall in the p series, there was always a number on the top and the n always was on the bottom. So while the exponent in general we would say is negative 1/2, in the case of the p series we just say that this is n to the 1/2 power on the bottom, which means that p is just positive 1/2. Sorry about that if that was confusing. I don't feel like remaking this video. All right, so the p value for the p series is 1/2. Since that number is less than 1, that tells us that it diverges. All right, so that means that we're doing the second situation here, where if we know that the middle one diverges, then the one on the outside would diverge as well. So let's go ahead and write this inequality here. I have 0 is less than this one, which is less than or equal to this other one. And if you think about plugging in infinity, then this denominator would be slightly smaller because you have the square root of infinity here, and then this denominator would be the square root of infinity minus 2. It would be smaller slightly than this one, which means that this one is a smaller fraction. And so here we're going to say since this one diverges, then this one would diverge as well. So we can make that conclusion. Or larger, not smaller denominator. Larger denominator. Meaning means smaller fraction, if you compare the two. Okay. All right, our third example, looking at this method, is we're going to look for 1 over square root of n plus 2 this time. So a very similar problem. We're going to go ahead and do the direct comparison test with 1 over the square root of n. And again, this is p series. I won't mess it up this time. It's p series where the exponent down here is a 1/2. So the p value is 1/2. That's greater than 1, so it means that that diverges. But this time, if we set up that inequality, we know that this denominator is infinity plus 2, so this one would have to be in the middle, and this one would have to be on the other side, right? So in square root of infinity plus 2 is a slightly bigger number. That means that this denominator is bigger, so this fraction is going to be a little bit smaller than this fraction. And this is not a conclusion that we're allowed to make. We're not allowed to say that it diverges out here, so we can conclude this one also diverges. If you guys remember from the example 2, when we do the divergent test with the direct comparison, we can say the middle one diverges, therefore this one diverges. So this is not a conclusion we can use. The inequality doesn't work in this situation. So when we write the inequality correctly, we are not able to come to a conclusion about divergence. So instead of trying to find something else to compare this to, we're just going to look at a different type of test. All right, so the different type of test that we're going to look at is the limit comparison test. Or LCT. And the limit comparison test says that if both functions are greater than 0, or both series are greater than 0, and the limit as n goes to infinity of the quotient of the two series has an actual number, so this is a positive finite number, so no infinities, it has to be an actual number, then a sub n and b sub n either both converge or both diverge. All right, so what we're going to do is we're going to take this exact same example, we're going to do it again with this new test. All right, so I'm still using 1 over the square root of n plus 2. Now I'm going to do the limit comparison test with 1 over square root of n. And I still have that conclusion that I had before. I still know that this diverges. So if I'm able to use the limit test, then I know that overall this is going to diverge as well. So I'm going to say the limit as n goes to infinity of this one divided by the other one. And before I can evaluate that limit, I'm going to do a little bit of simplifying. So I know that I just need to do keep it, change it, flip it. I'm going to take that bottom fraction and multiply by the reciprocal. And so that means what I'm actually finding the limit of is square root of n over square root of n plus 2. So we know that when we plug in infinity, that plus 2 doesn't do much to the infinity. And so these two are exactly the same. That means that this limit is ultimately 1. And since the limit is 1, that means the limit is a positive finite number. And this one diverges. And so our conclusion is that this one would diverge as well. let's do another example. So this time we're going to look at from 1 to infinity of the square root of n over n squared plus 1. And we're going to do a limit comparison test with square root of n over n squared. So they're very similar. Obviously the plus 1 is the only thing. The nice thing about this one right here, because right now you might be like, that's not recognizable, it's not geometric, it's not telescoping, it's not p-series, please don't make me do the integral test all the time, what do you want me to do? If you look at this, you can see that you've got n's on the top and the bottom. If we think of the top as being a 1/2, and we want to kind of combine our like terms here, we could rewrite this as 1 over n to the 3/2. So if I cancel out half an exponent from the top with half of an exponent from the bottom, then that gives me 1.5 on the bottom. So that means that this second one is actually a p-series, where the p-value equals 3/2. And 3/2 is greater than 1, so that means this converges. So if we were able to successfully do the limit comparison test and find that the limit really is a positive finite number, then we will be able to conclude that since this converges, this one would converge as well. So I'm going to say the limit as n goes to infinity of my first series divided by my second series. I'll go ahead and use this version only because it's a little bit more closely related. And then I'm going to go ahead and do flip the bottom one up. And if you can see here, those square root n's would cancel, right? And we would end up finding that we have the limit as n goes to infinity of n squared over n squared plus 1. Those are the same, so the limit here is 1. And that means we can make that conclusion that the series converges. All right, last example. So I might have a hard time fitting this. We'll see. All right, so I'm going to look at the series n times 2 to the n over 4n to the third plus 1. And I'm going to do a limit comparison test with the exact same thing. I'm just going to take away that plus 1. So n times 2 to the n over n to the third. Now, since I don't have the plus 1, I can do a little bit of simplifying here. I can call this 2 to the n over n squared. And this is one, it's not geometric, it's not telescoping. This is one where the nth term test would work really well. And that's because if I was to do the nth term test and kind of think about the limit as n goes to infinity of 2 to the n over n squared, I know that the top of this is going to grow much faster than the bottom. Exponential functions grow a lot faster than quadratic functions do. So that means that this is going to have a limit of infinity, which means that that diverges. So I didn't have to work too hard using the nth term test to see whether this diverges or converges. So that diverges. Now I can go ahead and do my limit comparison test. So I've got my first sequence over, I missed the 4 over here. Sorry, go ahead and put the 4 in there. The 4 doesn't make much difference anyway when you're comparing the infinities. All right, so let me go ahead and write this one. I've got n times 2 to the n over 4n to the third, and I'm going to go ahead and keep the first one and flip the second one. So these completely cancel because they're identical. And then I'm going to be left with 4n to the third over 4n to the third plus 1. And so I can conclude here that this is a limit of 1. And so since this one diverges, then the other one has to diverge as well.